Okay, so let's get started. Okay, so we're lecture 36. Um, and we only have two more lectures after this on chapter 17 before our exam. But the exam will only actually the exam will cover. It says 38 here, which is this lecture, but it won't cover this lecture. It'll only cover like Friday will be the last material that will be on exam 3. Yeah, I'll make that correction. Okay, so for review, lecture 35. So in lecture 35, what we did is we looked at a method to approximate the lower cutoff frequency. Okay, and so we looked at a common source type of circuit and some other ones. And what we did there is instead of like looking at all of the zeros and all the poles, we just looked at the circuit itself and did an approximation straight from that, because a lot of times, like we said, we are only interested in the lower cutoff frequency and the upper cutoff frequency. So what we did, we transformed the capacitors into different types of circuits where, for example, this C1, we converted this to some resistor 1S, and then we shorted the other capacitors here and here and made this circuit. And then from that, we looked at the circuit to determine what R1S is. We did the same thing with capacitor C2 right here, turn that into a resistor and look at the effective resistance seen by this port. And did the same thing with capacitor C3 from right here, from R3S. And then once we had all these expressions for these resistances here, here, and here, then we use this expression right here to determine what the frequency is for the lower cutoff. And that's just a sum of all of these right here. So it's 1 divided by RIS multiplied by CI, and that's the capacitor you're replacing. And if you want to convert the angular into hertz, you do it this way right here. Is divide that by 2 pi to get rid of the radians. Okay, so for this lecture, we'll finish off 17.4, looking at transistor models at high frequencies, and then we'll get into base and gate resistances in the small signal models, and also high frequency for common emitter, common source amplifier analysis. Okay, so finishing off what we did last time, we were looking at high frequency analysis for these transistors. And so we did for the BJT, the capacitors, there are capacitance that appears between the base emitter and base collector terminals of the transistors. And we're going to include that into this hybrid pi model called the small signal hybrid pi model. So typically these aren't there in our last hybrid pi model, but now we'll include them for high frequency, so we do have to put them there. We can no longer neglect them. So we have this C pi and also C mu, and we define C mu as this expression right here, which is I think derived in chapter 3. So we saw that. And this C mu 0, it represents the total collector base junction capacitance at 0 bias. And this phi JC right here is the built-in potential. It's typically between 0.6 and 1 volt. Okay, and also from chapter 5, the author is using this expression to describe C pi. So we saw that last lecture. And here's like the summary. So, So the shunt capacitances such as C pi right here, they're always present in electronic devices and circuits. Okay, so they're always there even though you don't explicitly put it there. At low frequencies, the impedance of these capacitors is usually very large, and so it has negligible effect relative to resistances such as this R pi right here. And as frequency increases, the impedance of C pi becomes smaller and smaller, and this voltage between the base and the emitter eventually approaches zero right here due to this right here. At very high frequencies, C mu shorts the base and the collector terminals together. So the whole idea of going through that analysis is basically to convince you that transistors cannot provide amplification at arbitrarily high frequencies because of these inherent capacitances right here. Okay, so let's now look at unity gain, FT. So the behavior of a BJT at high frequency, it can be found by calculating the frequency-dependent short circuit current gain, beta S. Okay, so we're taking this right here, from right here, and we're converting it to this, right? So this is the short circuit current gain, beta of the BJT. And as you can see here, it's a short circuit current gain, and here's the short right here. So this is IC. So that is being applied right here. Okay? And we also have this current going in here. So by injecting this current IB into the base, the collector current IC consists of two components. So this IC right here has this component right here, okay, and also this component I mu right there. Okay, and this I mu, you can think of it as, by Ohm's law, it's just this SC mu multiplied by the voltage BE across the capacitor right there. So since both of these expressions have voltage BE, we can factor that out, and so we have this expression. So this is for the this current IC right there. Okay, and now due to that short, these two capacitors are in parallel, the C pi and C mu. You see that? So C pi is actually in parallel with C mu, and the reason why is because it's short, it goes to this common ground right here. And also R pi is in parallel with these two together, C pi and C mu. So this right here is in parallel with this entire branch right here. You can see that. And so the base emitter voltage, BE, by voltage division, is this IB right here times this right here. So it's this resistance in parallel with this. So it's that times that divided by that plus that. Okay, and you can multiply top and bottom by this factor right here to get this expression. Okay, so this has your IB, this other expression has your IC, and then for your frequency-dependent current gain, it's just the ratio of these two, IC over IB, and that could be expressed like this. And you remember that what this beta 0 is, it's GM R pi, right? Now, the book says that because there's a high frequency transmission zero at this frequency, and you can see this frequency right here, so the frequency's in there. Now, for there to be a zero, the numerator to be zero, this, whatever this has to be, it has to be multiplied by this, and this whole expression here needs to be 1 to cancel out with that. So if the frequency here was GM over C mu, then this expression would become 1, and that's where you get your 0 from. Okay, so because of that, they say you can say that this is approximately equal to this expression. Okay, where it's just this alone, and that's for very high frequencies. Okay, so now this expression right here, you can cast it into this form right, by making the substitution of beta right here being 1 over r pi times c pi plus c mu. So that's what this expression is right here. Okay? And also if you want to put it in hertz, you write it like that. So this is called the beta cutoff frequency. Okay? That's what this is right here. And if you want to look at that, so this right here is a plot of this equation. So if you plot this equation right here, at low frequencies, it looks like this. So what that means is at low frequencies, this is nearly 0. So this becomes negligible. So it's just beta. And beta 0 is gm r pi. So that's what this is right here. Okay? And then at frequencies, higher frequencies greater than your beta cutoff, right? This is your beta cutoff frequency right here. Okay. Then it looks like a single pole roll-off. And of course, that's 1 order. So it's 20 decibels per decade. Another thing you notice here is that this beta cutoff right here, that's always going to be 3 decibels down from the max. Okay, so your max is sitting at gm r pi, your beta 0, right? So 3 decibels down from that is the point where you're having your cutoff. Okay, and this point right here, this is, we've seen this before in a previous chapter, but this is your unity gain. And that's where this part right here crosses through, right here at 0 decibels, which is amplification of 1. So in that case, you could take this, multiply the top and the bottom by your beta cutoff frequency. You'll get this expression, where now you have beta here, and also you have this omega beta there. This product right here is omega t, that's unity gain, or you can just write it ft. Okay, but that's what that is. And so it's equal to this beta 0, which is this height right here, and omega beta, which is from here to here. Okay. Yeah, so that's what this is right there. Okay. All right, so so the transmission 0 is actually greater than unity gain, because we said it was pretty far out there. So that's what this expression was, right? And remember what that was. The unity, that was to create a 0 here, right? So when S became this, omega m over c mu, then this expression goes to 0, okay? So that's what that is. So, and that's greater than this frequency of omega t right here. Okay, so we're talking like way out there. Okay, and also note that that the C pi is directly proportional to the collector current. So the C pi, it equals Gm over your unity gain, omega t, minus this C mu. But that, this transconductance right here is equal to IC divided by your thermal voltage, which is 1 over 40. So that's where this 40 comes from. But you can see clearly here, this is proportional to your collector current. Okay. All right, so so high frequency model for the FET. Okay, so for modeling the FET at high frequencies, the gate drain and gate source capacitances, and that's the CGD and CGS here and here, they're added to the small signal model. So here's the small signal model. and then we'll add these here. We'll do the same kind of analysis where we'll short it out here, and then we'll add this input current, same as we did before for the BJT. And we get the same kind of analysis too. So for the analysis, we have ID equal to this, where this VGS is factored out of there. And then you have your current gain, which is ID over IG. It equals this expression, and then you have this expression right there. And then from this expression here, you can see at DC, the current is infinite. Okay, so at DC, this expression goes to 0, so it's just this. And then so at 0 current, this blows up, this whole expression there. And as the frequency increases, as in S, then it falls off at a rate of 20 decibels per decade. So very similar. Now the unity gain, that's the unity gain bandwidth product omega t of the FET is this right here. And the FET current gain falls off, falls below 1 for frequencies that are greater than omega t. And in this case, the transmission 0 omega z is at this expression right here, which is actually greater than omega t, just like last time. So this is very familiar to the BJT analysis. The only thing is that at DC, it doesn't flatline. It actually goes up to infinity. Okay, so let's look at the base and gate resistances in the small signal models. So now this base resistance, we're going to call it Rx, which is right here. This is going to complete our hybrid pi description for the bipolar transistor. So this so the base current IB right here, it enters a transistor through an external base contact and traverses through a relatively high resistance region before actually entering into the active area. So you have this connection right here, and there's this physical connection, and every time you have this connection, you have this resistance. And so you have your current going through here, and this whole area, you can approximate it as being this effective resistance, Rx, which is quite high, before getting here. And so in our model, our small signal model, we have this expression, we're adding this expression to it, right? So just having, instead of just having B here, we have this base resistance, right, before getting to B prime. Okay, it says here that the circuit element Rx models the voltage drop between the base contact and the active base region of the transistor, and it's included between the internal and external base nodes of B and B prime. Yeah. Okay, so now this base resistance usually can be neglected at low frequencies, and for low source resistance applications, Rx can be a limiting factor at high frequencies. For a low noise amplifier design, the thermal noise within Rx, it could be a limitation. And the range of Rx is typically between a few to 1,000 ohms. Okay, now let's look at the same thing for FETs. So similar effect occurs in FETs where the gates of the MOS transistor are typically formed for metals or polysilicon, all of which have finite conductivity. There's also contact resistance between the connections of any other different layers in materials. So you have that throughout your entire transistor. And there's a gate resistance RG in series with the internal and external gate nodes of the MOSFET. So at high frequencies, RG limits the bandwidth, and for low noise amplifiers, the thermal noise limits RG. And this is the case here. So here's what we have for the BJT. Here's the small signal model we'll have for the FETs right here. But pretty much it's the same type of thing, right? You have this high resistance that you have to deal with. And also at dealing with low noise applications, the limiting factor here is going to be your thermal noise. Okay, so So let's look at the effect of base and gate resistances on this on mid-band amplifiers. So so what we did previously is we looked at these voltage gain expressions, but now we have to update them with this Rx right here. Okay, so and we'll do that a couple of ways. You know, we could just write it like this right here, and basically that we're just modeling it by just putting the Rx in there. Or what we can do is we can absorb this Rx into our pi and also the transconductance here. So that's why this R pi has a prime here, and the transconductance GM also has a prime. So they're slightly different variations from these over here. Okay. So so in that case, so the current generator and the model is controlled by the voltage V right here. Okay, that's developed across this R pi, and that's related to the total base emitter voltage VBE, which is right here. So this voltage V right here is equal to VBE times R pi over Rx plus R pi. Okay, and the current of the voltage controlled current source right here is just the transconductance GM multiplied by this voltage. And so just plugging this into here, we get this expression. And then what we do is this whole thing right here is going to become our GM prime. Okay, so that's what this is right there. Okay, so so by doing that, we have an expression for our R prime. So R prime is just Rx times R pi right here. So Rx plus R pi right here is this R prime pi. And for the GM prime, it's just this expression right here, which we got from this right there. Okay. Now, the current gains between these two models, this one and the one where we absorb the base resistance, they're going to be the same, of course. And here's a summary of the analysis for 3 different types. We have the common emitter amplifier, common collector amplifier, and also common base. We have the terminal voltage gain right here. We have this R pi prime for those right there, and our GM prime right here. The signal source voltage gains right here. Input resistances, output resistances, and input signal range and current gains for each one of those. Okay, so now let's look at high frequency of the common emitter and common source amplifier. So what we'll do first is we'll start off this analysis by looking at an RC circuit, right? And then we'll add some components to the RC, okay? So in looking at this RC right here, the V out, which is Rx over Vn right here, it's this. And you could probably do this just by inspection, okay? But so it's R2 in parallel with 1 over SC1, and over here we have R1 plus R2 in parallel with 1 over SC1. We can rewrite this like this, and what we want to try to do is get out a factor that's not a function of S, and then group everything else together that is a function of S. So that's where this comes from, and that comes from. That's why we're doing all the reduction here. Like before, we'll take this factor out in front to be the amplitude, the gain, in the mid-range. And this expression right here will be the high frequency component. So that's going to be your FH. Okay. And in doing so, of course, we replace the S here with J omega because it's steady state. So no sigma there. But this omega p here is being replaced by this right here. Okay, so that's why you have your omega p there. Try to normalize that. Okay, so here's our expression that we're left with. And if you were to plot it out, here's the magnitude as a function of frequency, right? And here's the phase as a function of frequency right here. And both of these cases right here, R1 was set equal to R2, and FP here is at 1 megahertz. Okay. Now, here's where we take a variation of this. So now that we did our RC analysis, now we're going to modify it somewhat. Okay, so what we're going to do is first do this, where we take this and then we add this component to it. Okay, so here's R2, right? And then we take this node right here, and we add onto it this amplifier with this feedback capacitor. Okay? And so we've connected it to this node X right here, which is all this node right here. It's all node X. And it has a gain of AXY. So that's the first step. And the second step, what we do is to take this and then modify that to be represented by an equivalent capacitor right here that's in parallel to ground with these other guys right there. Okay, so, and we'll stop here, but this is where we'll continue on Friday, continuing on with this analysis of how we are able to take this and then create an equivalent capacitor right here that does the same thing. Okay. All right, that's it for today. Actually, create an equivalent capacitor right here that does the same thing. Okay. All right, that's it for today. Actually, so this is actually separate, but I do want to ask you guys about something here. So during break, I'm going to have maybe 5 weeks. I'm going to be working on this project, and I want to get your input on it. So, some of you may know I'm working on this learning tool for students solving problems. And so, so let me just go over it real quickly with you guys in the amount of time we have left. Is a equation solver, and I think everyone's familiar with Wolfram Alpha, right? And it's an equation solver. Okay, but what I'm doing is something called a word problem solver, where it's going to be some software where you can get online, you can enter in your specifications of your word problem, and what it'll do is it'll show you step by step how to determine your governing equation. And it's kind of funny because if you think about it, an equation solver, that's assuming you already know your governing equation, right? So assuming you did all the work to find out your governing equation, and then you're going to solve for some variable. The problem I think most people have is not coming up, is not solving a variable for their governing equation. I think most people have the problem of actually coming up with that governing equation in the first place. Okay, so now it's called Pathway, and I'm doing it for thermodynamics right now, because it's one of the, there's many difficult courses, but thermo is pretty difficult. And this is a standardized test right here, scores for thermodynamics and different years. And this is a standardized test taken by civil engineers, mechanical engineers, electrical engineers. And you can see where the grouping of test results are. And this is a national test, right? That's 90%. Okay. And this just tells you, wait, who here has had thermo? Does anyone have thermo? Is it a requirement for ECEs? Oh, it is? Okay. Yeah, so maybe I can hurry finish it before you guys.
Yeah, that'd be nice.
Okay, so yeah, so that's a huge problem, right? And of course, what the ME professors typically do is they try to grade on a curve. Otherwise, you know, most people will not pass that class. But anyways, like so here's like a typical problem in thermo. Now I'm going to apply this in other classes too later on. But like I said, I'm doing it for thermo now. Yeah, okay, so I'm doing it for thermo now. So here's an example of where it's like here's a word problem, and with any word problem, it doesn't matter what class you're taking, you have some words surrounding your critical specifications, and your specifications are all you need. The words are basically just to make it more realistic. So here's the critical information that came out of reading this right here. You have a substance, it's an ideal gas. You have two states, state 1 and 2. You're given some pressure, temperature, and number of moles. You're given the work and heat for that process. And then you have this state, this pressure, state 2, and they're asking you to determine the temperature. So, so this is what happens if you use Pathway right now. So the whole program is in MATLAB, but I can put it online if I compile it, and that's easy to do. That's not a problem. So first you put in your analysis type. In this case, it's quasi-static, because that's what the problem is. Here's the specifications right here. Then you put in like the number of substances. Oops. You put in the number of substances. You have one substance. You put in more here, but it's just one substance. Then you put in a number of states. It's 2 states. And then you put in your other information, like your control volume. And I know since you guys haven't taken thermo, a lot of that stuff is kind of, you're not really sure what it is. Okay, but look at the big picture, right? Because when you take thermo, you know what this stuff is. So it's an ideal gas with variable specific heat, C, and then you put in these other things. You go to state 1 here, and I've listed in state 1 all possible things they can ever ask you about state 1. So you just scroll up and down until you find the things you need. So you got pressure, temperature, and number of moles. So you click those. Once you click those, the asterisk appears there, and then you do the same thing with the process. So you have the heat and the work. So you click that, the heat, click the work, and then for state 2, you click the pressure. Now this is the thing you're looking for. I have to like fix this problem here, but you also have to key that in too, which is kind of strange. But anyway, so once you've done all that, then you click on the kind of things you can find. You can find any one of these, but the problem is asking you to find T, the temperature. So once you press the Pathway button, then it tells you step by step how to find the temperature at state 2. And it also tells you the reason why you're using that equation. Okay? Everything that's underlined here is what was given to you in the problem. Because if you remember, it gave you the temperature at state 1, it gave you the number of moles, it gave you the work and the heat for the process going from state 1 to state 2. And also, this word problem solver, it's only showing you this first solution, but it's actually able to calculate, it actually calculates all possible solutions, all possible solution paths. And the one it shows you is just the first one that it found. Okay, but inside of it, it shows you many more. So the cool thing about it is that this is just like showing you like whatever, like what all these things mean. It's like it has its own nomenclature, so you can follow along. But you can also find other things. Like let's say you want to turn the problem around and you want to find the work instead. Let's say it gave you the temperature, but how would you then find work? This is how you would find the work then. Or let's say you want to find the number of moles. Let's say it asked you that instead. here's how you find the number of moles. You can move this around by just dragging and clicking on it, so you can see other equations. Yeah, and also like if you want to find the entropy, that too. Okay, so what I want to ask you guys is, since I'm going to be adding, to this over the break, like what other things would you guys like to see? Like what other features would you like to see in this to help you guys, like, if you, and this is like with the general class, not thermal. Thermal was just an example, but typically in your class, like, what are your biggest problems? Like when you are stuck on a problem and you need to break through, like what kind of help would you like to see in a software tool?
Maybe something that like helps me like visualize it better. Like if there's any kind of modeling,
like an image or something?
Yeah, or just something that, because I feel like one of my issues with some of my class is like some of the numbers and stuff like just kind of don't have a lot of meaning. So
That is something I've been thinking about too. Like how, because what this doesn't have yet is a picture, and I actually I've been thinking about a way to make a general picture of whatever you enter in. But so I'm glad you mentioned that, because then because sometimes I'll think of something like, well, is it just because I want it, or is it really needed? Right, so that's a good indicator that it's needed. Another thing I should mention this. A lot of times I think when people get solutions back, they'll look at the solution and they'll say, oh, that's how you do it. Well, that's only one way to do it, right? But the thing is that what you're really concerned about is how to fix your solution that you were thinking, right? Because like I said, this finds every possible solution. Okay? So that one that is showing you is just one of like maybe, 20 to 50 other ones that are just as valid. They have different number of steps, of course, different ways of getting it, but they're all valid. And so the thing is like, how do you find out where you took a wrong turn in your own personal path that you chose, right? Instead of looking at someone else's solution that the book author made, or the instructor made, right? So one thing I was thinking about adding is like, instead of just showing everything all at once, basically showing one step and then saying, okay, here's that first step, and here's like 5 other possible ways you can go. Which one do you want? And then you click on that, and then it takes you to the next level and says, okay, well now there's 3 possible paths you can go down. Which one do you want? And then basically, if you follow that process, you're basically entering in every single step that you personally made, because it's going to have your solution in there somewhere, right? But that's how you can find out your path, and then eventually you'll get down to the step where you took a wrong turn. And then you're like, oh, I went here, but that's not valid, because I should say here, I didn't talk about this, but this is like a list of assumptions. And every model has to have assumptions, right? And so the reason that all the paths are valid, because they all apply, these assumptions are valid for every single path. Otherwise, it'd be even, a lot more solutions would pop up. But they're all valid, right? So maybe there was something in the problem that you didn't consider, and you used a wrong equation. Like it was ideal gas. Maybe you used an equation that had pressure in it, but it was not for ideal gas, and you forgot about that. I don't know, but what else? Oh, wait. First of all, with that idea that I just talked about, is that something that you guys would like to have in there? Yeah?
Because a lot of the times professors will have like a way that they want it to be done on the test or whatever. And so you really need to be able to understand the way they do it. So understanding one solution is good, but understanding how they do it on the problem.
I see.
So
Yeah,
if you
yeah.
can go through and like, oh wait, he wants me to do it this way, but I'm not quite sure why. But then you follow the steps on that.
Yeah, yeah, exactly. Yeah, because it does show you why.
Right.
And it's kind of funny. Like, I remember back, well, even now. so when I see solutions from authors, they don't explain their steps.
Mm-hmm.
They don't explain at all. And also, they don't start off with the unknown. They'll start off with some, because they're so used to finding out. I mean, they're so used to the material. They'll immediately jump into the most effective or the most efficient route.
Mm-hmm.
In Pathway, everything starts off with the unknown. I don't know if you guys seen this, but for everything you choose here, that's where it starts off. It starts off with the unknown, and then it goes from there. Okay, so it's logical. I mean, you can reorder these things, which is what the book does, you know. But you know, someone else, did you raise your hand?
Just talking about the branching options for you to be able to, once you have chosen a path, go up and click another one, and then just offer.
Oh, like okay, have like the opportunity of looking at other paths. Well, yeah, that'll be interesting. Like, yeah, so like as you're going down and clicking your preferred method, you can go back up and say, okay, what if I did this way instead? Yeah, that's actually good, because I think what that will do is give you guys a broader understanding, because like I always make this analogy, right? So piano players, when they're learning how to play piano, they will practice their skills, and if they get something wrong, one note, they'll know immediately, and they'll be able to correct it. If you're trying out for the basketball team and you're shooting free throws and you miss, you'll make a correction right then and there, right? I go on and on for all kind of other majors where there's immediate feedback, and you can have unlimited practice, and that exists in so many other majors, but not STEM. You cannot practice very efficiently in STEM, because if you like, there's lots of problems in our textbook, but if you start doing those problems, how are you going to know if you're right or wrong, right? It's not like you can go to the professor and say, hey, can you give us all the solutions? You can work them all out or whatever, because so you only have access to, you know, the homework problems that are given to you, and it's a small number, so it's really not that much practice. So all you can do is just practice that small subset over and over again, and it's really hard to venture out. You can if you want to, but you'll never know if you got it right or wrong, which is a problem. This right here should be a really good practice tool. And because it's online, you'll be able to access it through iPad or your phone as well, because it's going to be available through a web interface. So yeah, the practice will be there. So 10:50, anything else? Any last minute comments, suggestions? Okay, cool. All right, I'll see you guys on Friday.